Suppose you could make one out of a jet ski. Have all the things you needed on it, as for this little raft that goes behind it on the umbilical. So you can check whether our assumptions were right. The diameter of the jet, we used a single diameter jet at 100 millimeters. Do you guys think in metric? How big is 100 millimeters? 4 inches. 300 millimeters is a foot. 1,000 millimeters is a yard, a meter. 300 millimeters a foot. 4 inches is that's 110. Yeah, it's 100 millimeters, 10 centimeters. So I wouldn't be surprised if that umbilical, the orange one, is of that diameter, which we've used. But we assumed the one jet, just to make life easier for that calculation. So, and it turned out to be a reasonable number, 16 kilowatts, right? 26 horsepower. What's a muscle car horsepower? 300 horsepower, something like that? Okay, give me a number. Don't make me guess. It is, right, of that order?
Yeah, like most normal trucks these days are around 300.
Yeah, fine. A 150? Okay, yeah. So 26 is a tenth of that. Not so big. So, kind of interesting, this squirting in front just to keep your balance as you're leaning forwards. Yeah, quite elegant, especially the underwater stuff as well. Anyway, so that was kind of a fun thing to do last time. Enough. Not sure I like the music all that much. Anyway, so yeah, this was interesting actually. This is a website that does all the pipelines in the US, which I thought was kind of interesting. And it's interactive, so you can turn them on and off. So perhaps you can see the key. So gas transmission would be natural gas, not car gas. Hazardous liquid, I have no idea what those would be. So now the big thing, the big contributor areas for those, Marcellus will be up here, Barnett Shale and different shales in Texas. I don't know why that's stopped. Where's my pointer? Oh, there it is. And going around the country, LNG plants would be on the coast. The big thing now is exporting gas, refrigerate it so it's a liquid, and then take it across the ocean to Asia or to Europe now, right, with the whole Russian gas thing. Incidents, interesting. Oh, there you go. Don't know how serious the incidents are. Don't know what the difference between incidents and accidents are. It's very bit squiggly. So lots of accidents. Maybe one of them is the San Bruno one that we looked at the other day with flames coming out of the ground. Not sure what else. Yeah, so that's the main one. So lots of pipelines. So even though I say pipes, which we're doing now this week and last week, are not so exciting, kind of formulaic, but they are important. It's not just the pipes that you'd have in your house that supply water, but that actually keep any nation going by supplying energy to the places where it's needed. Specifically in the Northeast would be the big population center. And here in upstate New York and northern Pennsylvania, there are lots of storage locations, and I guess that segs into this, which I was trying to explain before. And the whole idea is don't know if this will come up or not. Just randomly choosing one. Yeah, it's good enough. Are salt caverns. So a big thing in the new transitional economy, energy transition economy, is what happens if you have lots of renewables in the grid, because you make lots of power in the middle of the day when the sun shines, and maybe you make it whenever the wind blows as well. But if you don't have capacity to use that, then you have to store it. You can't just get rid of it, and you don't want to waste it. And so typically you want to store it, and one of the ways to store it would be by using hydrogen. So you take water, you'd use electrolysis to split it into hydrogen and oxygen, you keep the hydrogen, and then when you need power, you just either burn it or use it in fuel cells to be able to do that. But to have grid scale storage, to be able to have, for the whole of the country for a few hours, you need very large amounts of storage. And so one way to store it is in salt caverns for hydrogen, or in actually aquifers or in depleted petroleum reservoirs. Salt caverns are great because they're absolutely kind of sterile. Nothing contaminates it. You make the salt cavern by just drilling a hole, putting a casing down, circulating water in that casing down a central pipe, and then in the annulus between the pipe and the casing up to the surface, and then by that retracting the whole casing and making a big long cigar. And then once it's built, then you have these cigars in place, and you can just pump water into them, brines from the surface, and allow those to be pumped out as you pump gas in. And so on a 6 or 12-hour cycle, you can get natural gas out of the system in the Northeast to supply New York City and the population centers in northern Pennsylvania and New York State. And you could also use them for hydrogen if you wanted to. And also the Strategic Petroleum Reserve, which is I guess it's petroleum that's stored. It could be crude oil, I guess, but it might be petroleum because it's more valuable if you refine it and put it into salt caverns. And those are all in Louisiana. And so when price of gasoline goes up, sometimes the president will tap into the Strategic Petroleum Reserve to put relief on price of gasoline. And so that has to be supplied by pipes into the ground, bringing fluids out of the ground, and also distributing stuff around the place. So, yeah, liquid pipelines. Bless you. And so they have some inherent risk with them, pipelines. And I told you about the Burroughs Street one that was going to supply power to the former coal-burning steam plant on the corner of Burroughs and College, which the residents objected to because they didn't like to have, I guess, a bomb under their road, which it can be. Okay. What else? Oh, yeah, something else today. You're not old enough for this yet, but as you get older, you tend to... I have this nostalgia thing in the morning where I look to see what I was doing this date X years ago. And so today, what is it, the 11th? Well, it's dangerous to do this because you never know what might come up. But here you go. We talked about pitot tubes. Yeah, I just noticed this morning. So if you ever go on a plane, it's kind of rudimentary that you'd have such a low-tech feature on a plane, which is when you know that Strava in your pocket or Garmin on your wrist can tell you exactly where you are using GPS and also tell you your pace as well. But the reason, what it can't do is it can't tell you what the airspeed is around your plane. And of course, knowing where you whether you have fuel left or how to fly the plane depends on your airspeed. And so this is just a pitot tube. So it's a forward-facing tube. It's where you just in front of where you get on the plane. It's got a core inside it, so that where the stagnation hits here and the velocity stops of the air that's going past it, it builds up pressure, and it compares it with a port on the side of it, which only sees the atmospheric pressure without killing the velocity. And so by comparing those two, it can get your airspeed, which is what you need to be able to fly the planes. And I don't know whether that one is heated or not. You remember the story of the Air France plane that had problems flying from Rio to Paris because it iced up and couldn't work anymore. So that's it. Good. So, don't know what that is. I hate those things. Presentations are due, so we're week 11 right now, as you see. Presentations are due on the Sunday of Thanksgiving beginning of Thanksgiving break, so you don't have to agonize over it over the dinner table on Thursday. Yeah, and that. So you should be thinking about that and talking with your groups. I don't think it's a very onerous project. It's just you've got to organize things so that you meet and then go away and do what you're doing. Okay. Anything else we need to take care of? Big class today. Got big. Have no clue of what?
Figuring out why half the class is missing.
They're always missing. Missing in action. I'm always curious whether they look at the stuff online. To me, yeah. So it's I don't know if I guess my message to you is given by video, wasn't it, this year, because I was out. But the message is that this is a self-run class. People do as they wish. We supply information for people to do in class, out class, as they wish. So, and then most of the stuff is on the assessments, as you know. So pipe flow for the second week. So we've talked originally about the jet lev, I guess. That was our example last time. So I thought it was kind of a cool example to do. This is what we ended up with. The sequence is just we needed to figure out what the velocity was that came out of the system to be able to hold a person up. And so once we could use a momentum equation for that, we could calculate from the velocity a Reynolds number. If we know a Reynolds number, we can calculate what the friction factor is. And if we have a friction factor, we can write the energy equation and solve for the pump head. And if we know the pump head and the flow rate, which we can get to in just one step, we can find out the power that we need to be able to run it in watts. And the calculation sequence was this. And so if you remember that, just before we head on, this was the elevation of the jet lev above the water, 1 meter height. This was the velocity term coming out of the nozzle. This was the head loss, major losses in the pipes, and this was the head loss in the fittings. I guess I was going to mention the fact that usually the reason that we call these major losses HL major is because they're quite large. They're small incrementally, friction factor, but over a long length they're quite large. Here they're not very big. They're only equivalent to the minor losses and also I guess the velocity of the fluid coming out of it. But if you imagine the length of this, instead of being 10 meters, being 100 meters, then this would indeed be 10, and this would be 12. I had this wrong. For some reason, it's 0.1 squared. It's 10 squared, so it's 100. So 100 over 20 is 5, which is the right magnitude here. So if you had that, if you were writing notes last time, that was wrong, my error. So in other words, if this was 10, then this would be 12, and this would be 5 times 12, which is 60, right? And so this would be 60 plus 1 for this, and then it would correspondingly, if this was 60 instead of 16, then it would increase this by a factor of 4 as well, right? So instead of being 16 kilonewtons, it would be 60 kilowatts rather. So anyway, so that's how to dimension things. So that's a straightforward expression. A so-called, we didn't refer to it as this, but a so-called type 1 problem. The last parting shot that I had before we packed up last Friday. So what will we do today? We talked about friction factors in pipes, in fittings. And so maybe today we'll talk a little bit, I don't think we'll talk about turbulence, but we'll talk about non-circular sections. And then we'll talk about these 3 different varieties of types of flow. And very straightforward, but let's do the first things first. So we want to be able to use the Moody charts. And so perhaps it's worthwhile drawing. You know what the Moody charts look like, and you know the principal features. You know that they're split with Reynolds number, velocity, density, characteristic dimension, viscosity. And they know that they're split by a friction factor, which we said is an Euler number. We know that there are a couple of different demarcations here. This is 2000, roughly. And this is turbulent. And this is laminar. We know that there's kind of a transition in there. We know that on this side of the transition, these are all a function of relative roughness. And so this is large magnitudes of roughness and small values of roughness, relative roughness. Bless you. And we know that this characteristic line is a friction factor which is equal to something over Reynolds number. Clearly it varies with Reynolds number. This is usually a log scale. This is a log scale. So 1-to-1 log Reynolds number to the log friction factor would be just a single. They look the same on a natural scale as well. And for our circular pipes, this calibration coefficient, it's working very slowly, is 64. And we can get that from the flow in a pipe equation. If we solved Navier-Stokes, we didn't do it, but we quoted the result. It's the same result that you might use if you're looking at bundles of capillaries to represent a porous medium and to get a permeability out of it. And I guess the final thing that, this is really slow moving around today, my pen's kind of lagging, is that these are a function of relative roughness only, horizontal, and these are a function of Reynolds number only. So this is for any roughness you could imagine. And the reason for that is that if it's creeping flow, it doesn't have the roughness that triggers the turbulence, which can't happen because it's creeping flow, and therefore these are, actually this is for all epsilon over d. It can be smooth, it can be rough. You remember that when we did our jet lev, I think we came up here, we assumed kind of that there's a lower bound here, which is a smooth, which is epsilon over d equals 0. So if you write that down, I'll just scoot back to this and kind of show you on a real Moody chart, which we have somewhere. Not there. There. So this is the real Moody chart. And so 64 over Re, there's some kind of transition. The smoothest of the smooth, this is epsilon over d equals 0, which goes down here. And these are the smooth pipes and progressively more rough pipes. We chose, do you remember what our Reynolds number was? I think it was 10 to the 4, wasn't it? 10 to the 6. So we got from using 10 meters a second a Reynolds number of 10 to the 6. And so 10 to the 6 would give us this. And we used 0.011. So that's the case there. If, for instance, it was 1% roughness, so we have a 100 millimeter diameter. If we had 1 millimeter of roughness on the edge of that, it would be this. And if that was the case, then our friction factor would be then bigger by maybe a factor of 3.5, right? And so what this would mean is that the drag in the pipe would be more by a factor of 3.5 on that central term. And so we'd have to accommodate that. So in other words, this term here, instead of being we took it as 0.1. We took it as 0.01. If it goes to being 0.03, then it increases it by a factor of 3. And it would come up even if it wasn't any longer. And so that's just in the calculation. So obviously, you want to have the pipe as smooth as possible. I'm not sure it'd be super smooth because that's really a glass pipe, but it would be something. So anyway. So that was, let's put that one to rest. What are we going to talk about? So what we might want to do, in the same way that we talked about the loss coefficients in pipes for K sub L, what we did de facto here was that these were all, by definition, turbulent. The assumption was that we're on that part of the curve. And so if you look at the Moody chart, that looks like this. Everything for these fittings was to the right of this term, the assumed roughness. If we want to do the same for non-standard sections, then we can certainly do that for laminar flows by using corrections for this C value, which depends on the shape of the section that we have. And so one way to do it is to both define what those characteristic parameters are. So in this particular case, you could imagine that if you had a pipe that had an annulus around, this would be the pipe that would be flowing down into the salt cavern. Not that I thought of that. The outer one would be the casing that goes down it. The inner one would be a pipe that would pump water down, dissolve salt, and then bring it up through the central one. They're separated from each other, for instance. And if you wanted to know what the, obviously the friction factor for the circular pipe would just be for a circular pipe, but for the annulus around it, it's controlled by the relative magnitudes of the two diameters. If D1 goes to 0, then it would asymptote, I guess, to 64, right? Because that is the one for something without anything in the middle. And so 0 would be 64. And I guess it's interesting that if it's equal to 1, so 1 would be, so it's just a thin film that's inside here. And you can imagine unrolling that, unpacking that thin film into a long, flat slice. And the friction factor of that is 96, which would come out of the parallel plate solution, which we didn't develop. If you have one that has a segment on it, and I should mention here that these are by definition for laminar flow, all for laminar flow. So it's this function C over RE, which we use in the Moody charts. If it's shut off for some reason because it has a flange on it, then if the angle of this flange alpha is 0, then it's 64, no surprise. And as the flange gets larger, it's less than that. If it's a duct, you can calculate it to be able to use the Moody charts that we have, or to be able to use the fact that friction factor is a function of C over RE, laminar. These are only laminar. It's important to know that. Then we can get what the equivalent hydraulic, this would be the value of C in this column. And the other parameter we'd need to figure out would be if we have a rough pipe, even though it doesn't matter for laminar flow, or if we had needed the Reynolds number, which we would need, then we need to have a characteristic dimension that goes in here. What we had used before was the diameter. If there's no annulus, no central pipe in this, is just the diameter. But the characteristic dimension would be the hydraulic diameter in this particular case. And the hydraulic diameter is just given by 4 times the flow area divided by the flow perimeter. And so this would be equal to, for a circle, it would be equal to 4. The area of flow, if there's no annulus, would be pi d squared upon 4. And the perimeter, God, this is slow, would be pi d. And so this would be, you've guessed it, d. So for a circular pipe, the hydraulic diameter reduces to the diameter of the pipe. It's kind of interesting. We'll talk about hydraulic radius when we talk about open channel flows, and it doesn't echo the radius of the system. And so if you want to use a characteristic dimension, you'd use that in this particular case. So it'd be God, this is really, this would be the area, cross-sectional flow of the area, and the perimeter would just be the area around it in each case. And I guess this is the magnitude that's marked here. So we can always use that to figure out those for any shapes you could imagine. Okay? So what else do you want to do? So, one example. It's not rocket science. It's a much easier sample. than we've done before. So maybe let's do one example, and then we can go back and talk about these other types of flow solutions that are talked about here. Sounds intriguing, but it's really quite mundane. So here's an example looking at air flowing along a duct. The duct is 0.3 of a meter by 0.15 meters, so we've got the size of it. We have a flow rate of, this is really painful. I don't know what's running in the background. Okay, just disappeared. Sorry about that. Hopefully it'll come up. Yeah. Not very useful. No, not bad. So yeah, so I don't know. Let's see what the last thing it remembers was. Didn't remember my last scribbles, so that's fine. Perhaps it'll be faster. We will see. Okay, so anyway, not rocket science. We have size of a duct, which is given in the figure on the right. We know that this is equal to the flow rate, which is what we would call Q, head loss in the duct. And so what we need to do is we would draw Bernoulli between upstream and downstream. We'd make life easy for ourselves by figuring out what the different parts were. So this would be into the page. And if we keep it at the same elevation, then Z1 equals Z2, so I don't have to worry about that. P1 would be greater than P2 because it's driving flow. And what the velocities be? V1 is equal to V2 because the cross-sectional areas downstream and upstream are the same. And so if we rearrange the energy equation, we'd end up with only P1 minus P2 divided by unit weight is equal to sum of HL. I won't write HL, but it would be friction factor, length over equivalent diameter times V squared over 2G. So that'd be the equation. So, and this actually would be the head loss, right? This is HL. And so we know a velocity. We know that velocity is equal to volumetric flow rate over area. So we have this, and we have this, and we have this. So we know that this is the average velocity in the pipe. We know gravity. We know the length is 12 meters. We know the hydraulic diameter. The hydraulic diameter would be what? It would be equal to 4 times area over perimeter, 4 times 0.3 times 0.15 divided by 2 times 0.3 plus 0.15. Right? So perimeter versus the shaded area. And if you have those, that's all that's going on here. If you have that, you can calculate, a roughness. I guess we haven't really talked about that, but you know how to do that. I think when we introduced Moody charts. There was this calculation to be able to get this. So roughness of different things, just from a table, you can get a magnitude of roughness either in feet or millimeters. 0.15 of a millimeters is very small. If you divide by the hydraulic diameter of the duct, then you get the E over dH. This is just a table that gives you this magnitude if you have, in English units, I guess in metric units as well, a relative roughness if you know what your tubing is and you know what your diameter is. So, but you can calculate that just by knowing what epsilon is and dividing it through by a diameter or hydraulic diameter. So that's where that comes from a reference table. And what else? And you need to calculate Reynolds number. Is equal to velocity, which you know, is equal to the density of the fluid, which I guess is air. And you need to know a characteristic dimension, which is dH. And you need to know the viscosity. And they just, what's used here, this is dynamic viscosity. I'm running out of space, but dynamic viscosity is equal to mu, which is equal to, for air, would be roughly 10 to the minus 5 Pascal seconds. Always remember that 10 to the minus 3 is for water, 10 to the minus 5 is for air, so 2 orders of magnitude. The kinematic viscosity is what this mu is. Just a definition, which is equal to mu, which is equal to dynamic viscosity over density. You see, this is Reynolds number, velocity, characteristic dimension, density over viscosity. This is just replaced by this value here. And so those are units. Calculate the relative roughness since you know what dH is, and then everything else just goes in to be able to calculate that. So V squared over 2G, friction length over diameter, and the friction factor comes from this relative roughness and the magnitude of Reynolds number. So just by going back to the Moody charts. So that's it. So it's just the same as we did with the JetLev, a so-called type 1 problem. So that's perhaps all we'll do on that. So let's talk about the other types of problems. Sounds mysterious, but these type 1, 2, and 3 problems are straightforward. And it's easy. You've already seen the diagram that defines them. But if you take the parameters that define the problem and define them between the geometry, the flow rate, and the pressure, and so the geometry would be epsilon, length, diameter, I suppose would be, or the ratios of some of those. The flow rate would be volumetric flow rate or velocity, average velocity, and the pressure would be either delta P or P. Then this mysterious classification of type 1, 2, and 3 merely depend on what you want to determine. So I guess in type 1s we know the geometry and the flow rate, and we want to determine what this is. In type 2 we want to calculate the flow rate if we know the pressure and the geometry. And in type 3 we want to calculate the geometry if we know the flow rate and pressure. That's all. It's the mystery. The one that we've already done is type 1. You remember that we had a person dangling on the end of something, so we need to calculate what the velocity was that would keep that person in the air. And so that gave us a flow rate. We decided on a pipe size because we saw it in the video, 4 inches, 100 millimeters. And we like the pulp. We know roughly how long it is, and we like it to be smooth, so we knew what the geometry was, and we knew velocity. And so what we did was calculate the pressure, the flow rate, and we also, from that as well, I guess, we could calculate what HP was from the pressure that we had to apply. Pressure is applied by the pump, and the magnitude of that pressure is defined by how much pump head we have to add in to juice the system. So the problem with the other ones, not the problem, but the issue with the other ones is that if we don't know the velocity going in, then we don't know the Reynolds number, so we can't calculate the friction factor definitively because we have to iterate to be able to get to it. And so that makes these other cases a bit more challenging, but not particularly challenging for us because we're good, right? So what I might do, if I can get out of this, is we might go and look at some of those examples. And I want to get back to this. And I'm not sure if this is the one. Yeah. Yeah, it is the one. Let me do that. Okay, so this is all the stuff above this you've seen, right? So this is our Moody chart that we have. This is what we did last time. We talked about writing the solution between upstream and downstream, and now we've just talked about this, determining the head loss for delta P, the ones we've done, and these two other ones that are different. So we use the same protocol as before. This is just another example to illustrate how we might solve the problems in different ways. In this particular way, this is what we did for the JetLev. So if we have a pipe, it's of length L, it's of diameter 10 to the minus 2, 1 centimeter in diameter. We can always get these behaviors by going through the calculation sequence that we talked before, was if we know what the velocity is, we can always calculate a Reynolds number. If we have a Reynolds number, we can always calculate a friction factor. God, this is painful. If we calculate a friction factor, we can calculate a head loss. And this would be the equivalent of our delta P. This is the end of our calculation. If we had to iterate, we could think of the fact that this calculation sequence is what we do again if we didn't get the answer in one solution. But we might think if we didn't have the velocity, we might have to join this calculation somewhere else by making a guess of what the friction factor was. So if we're talking about these other type problems where we don't necessarily have the velocity coming in, we might have to either assume a velocity or calculate a ballpark of a friction factor we expect and then work from that. And so in type 1 problems, we can start here and go through this logical sequence and we're done. In type 2 problems, we might have to jump start it by guessing this, calculating a head loss, from that head loss, calculating a velocity, using that velocity to calculate a Reynolds number, and seeing if the friction factor we've chosen is actually correct because we just guessed it in the first place. It has to be in concert with whatever the Reynolds number is. So that's the calculation sequence we will do. I think this first calculation sequence, which is an old class where it's been done, is just to go through this. So choose a smooth pipe. Head loss is given by this. We need to know the Reynolds number. Reynolds number is given by this. If the unknown is the velocity in this, then we can calculate Reynolds number as being this. Diameter of the pipe, density of water, viscosity of water. And so that gives us a Reynolds number in terms of a velocity times 10 to the 4. It's not dimensionless. You have to use velocity in terms of meters per second, and then multiplying by seconds per meter will give you the non-dimensional Reynolds number. And so if we choose a laminar system where we have a small velocity, then 10 to the minus 1 times 10 to the 4 will give us 10 to the 3, 1,000. We know that the crossover point for turbulent is something like 2 times 10 to the 3. So we're still in this zone here. And so I guess we'd go through. We have a Reynolds number of 1,000. If we use 1,000, we could calculate what that Reynolds number is. Be this. Didn't mean to, right? And it would be 0.062 or something, right? I would guess. So I can't imagine we use it to that precision. Okay. I guess this is 0.064, which we could use directly in this. Or if we wanted to, we could just substitute 64 over RE. This is just equal to the friction factor. We've just read that friction factor off the chart, which is this, but we could also calculate it since we have a Reynolds number, and I guess 64 over 1,000 must be 0, yeah, well, I guess it is, right? Even I can do that one. 64 times 0.001 is 0.64, and we get, as a result of that, the head loss. If we're in the turbulent regime, then we can just jack up our velocity. We know that we're at 1,000. We know that we transition to turbulent at 2,000, so we could just double this if we wanted to. So certainly multiplying it by 10 will get us there. So 1 times 10 to the 4 gives us a Reynolds number of 10 to the 4. If we're at 10 to the 4, then we're going up here. I guess it's already marked from past time. And the magnitude would be 0.029, I don't know, something like that. 0.03. If it's a smooth pipe, 29, I guess. And you then put that into this expression as we had before, and are able to use it. And if it's a rough pipe, say 1 in 100, just as we did for the jet lev, I guess we'd be going up to wherever we intersect this curve here, which is exactly this. And instead of being 0.03, it's 0.042, something like that, which is the other. And so, yeah, so that's just a calculation sequence. In the case of laminar flow, we can use this, because this is an exact solution, and it varies with Reynolds number. For this, the friction factor is independent of Reynolds number, because the curves are all horizontal, or mostly horizontal. This one has a slight curve in it right here, but in the true turbulent regime, they're horizontal, and you can just use the friction factor straight. And if you do that, you get magnitudes. Friction factor doesn't change by very much, but the head loss, you see, changes by a big amount. Head loss is 0.2 meters versus 3 millimeters. So having said that you don't have a good feel for metric, 3 millimeters is, 0.3 millimeters is a tenth of an inch, something like that. And 0.2 of a meter is 8 inches. Right? 0.3 of a meter is roughly a foot, so 0.2 meters is 8 inches. So this changes in a big way. And the reason for that is that if you look at the scaling of this, that the head loss is proportional to the velocity squared. So if you increase the velocity tenfold, then you increase the head loss by tenfold squared. And so this is the reason that it turns out that way. So that's why it becomes much larger. So even though the friction factors don't change very much, the linkage between head loss and velocity takes care of that magnitude. So what happens if we want to do this for a problem where we do this so-called type 2 solution? So type 2 means that we want to figure out what the velocity is as a function of knowing what the pipe system looks like, its geometry, and as a function of knowing what the pressure drop between upstream and downstream is. And so we have to join the calculation scheme partway through and maybe choose a guess of a friction factor. That's quite convenient if we assume it's turbulent, right? Because if we know what the roughness of the pipe is and we assume that we're turbulent, we always know what the friction factor is because they're a unique function of each other. It's not so easy if we're in the laminar regime. And so I didn't look in great detail about this. So for that same example, what we can do, so this is now a centimeter diameter pipe. It's a meter long. We want to calculate what the velocity is if we know what the head loss is of the system. I guess I might be just taking a random number. It was 0.2 of a meter here. It is less than that here. So I'm just taking a random number to be 0.1 of a meter, which is 4 inches, right? So choose a roughness, 1 over 100. Choose a head loss. We can use this to rearrange this. So rearrange this equation in terms of v squared. Take everything off to the left-hand side. Multiply by 2g times d. Divide by friction factor over length. You get this. Take the square root of both sides. You get this. And so now, if we have a friction factor that we can put in, we can calculate this for v. The easiest way to get the friction factor is to choose it for the roughness, which is 1 over 100. Kind of small here, but if you see this directly here, 1 over 100 gives us 0.038. I'll get rid of that. If you put 0.038, did I say 038? It is, yeah, 038. Or 0.04, and then do the calculation. It comes out that you get a velocity of 0.7 meters a second. If you calculate from the Reynolds number we said is 10 to the 4 times the velocity, where the velocity is in meters a second. So 10,000 times 0.7 is 0.7 times 10 to the 4. So I guess that's 7 times 10 to the 3. This is 7,000. So that would be 0.7 times 10 to the 4, somewhere here. We go up to that same curve. This is the same one. That would give us a revised friction factor of, I don't know, 0.4046, I'm guessing, something like this. Which is this. And so now we want to see if this really is the correct friction factor. So repeat the calculation by substituting that friction factor in here, calculating what the velocity is. All this is that the velocity is equal to this, which is 0.66 meters per second. That's this. 0.66 meters a second times 10 to the 4 gives us 6.6 times 10 to the 4. 6.6 times 10 to the 3. .6 times 10 to the 3 is basically the same line as before, so it doesn't change. So we've kind of iterated to a single solution. And so the actual Reynolds number is this, and the head loss, the velocity that we've calculated is exactly the one that we've got here, which is 0.66 meters per second. That's it. So if you go back to kind of the mnemonic of, I guess not mnemonic, but the sequence of what we were trying to do is we've tried to do exactly what we said. This is always the calculation sequence, except we can't join it at the beginning. We have to join it partway through. If we know what the relative roughness is, then we can get friction factor straight away if we assume it's turbulent. If we have the friction factor, we can calculate, I guess, we know the head loss in this particular system. So we can calculate from that the velocity. If we know the velocity, we can calculate the Reynolds number, and we can check the friction factor. If the friction factor isn't the same one that we used before, then we have to reuse again the head loss, which we were given. It was 0.1 of a meter. And then we have to go back to calculate the revised velocity based on a revised friction factor, a revised Reynolds number, and then check until we get this solution. So that's it. So that's the calculation sequence that we've done. Yeah, I guess that's it here. And so that's exactly what we're doing. We're assuming it's turbulent because we can get the friction factor from the geometry alone. If we use that friction factor, then we can just go through the sequence multiple times where we give head loss. That's about it. Talk about the other one next time, probably. Clear? Clear as mud? Too easy? Fine. Nicholas?
So pretty much we use each case to we rearrange the same equation based on the scenario, and then also use that.
Yeah. And I guess the other thing is you'll note that when we did this head loss equation, here, because it's turbulent, it ends up being a function of velocity squared, which we square root. If you look at the laminar case, it turns out being a function of Reynolds number turns up in here. So because Reynolds number has velocity in it, one of the velocity and the velocity squared terms drop out. So if you rearrange this equation here, it's a function of velocity, not velocity squared. So yeah, you rearrange the same equation, and it just turns out differently. Pipe flow is exciting, don't you think?